Good afternoon. Any questions? Any comments? So I want to finish this chapter by introducing some more abstract terminology and like some formalism, and I'm going to close it here. So I will talk about vectors, operators, and more Dirac notation. So you may have noticed that so far we were making a big fuss about wave and particle, right? Or things were like sometimes wave-like, sometimes like particle-like. But like now we introduce some like more formalism, right? We have like operators that may or may not commute. Like x is a position, right? Momentum is momentum, and we promote them to operators, and then they happen to not commute. And in our formalism, if things do not commute, they cannot be observed simultaneously, right? Then wave-like or particle-like, it actually doesn't matter. The real thing is like you have like a state, right? We have a quantum state. So I want to call it like this Dirac notation ket. I will write it like psi sum of psi of t. And this is like an abstract state. No matter what we do, right, people perceive this to be the state of the system. And if you look at it in different bases, you are going to get different results. And that I want to expand this in this hour. So this state is an element of Hilbert space, and it obeys Schrödinger equation, right? I h bar. So I'm also going to write it in abstract form. I'll talk about this later after I set up what I mean here. Psi of t is going to be h psi of t. And here h is an operator that I am going to talk more in a little bit. Now, so this is the state, whether we are in real space or momentum space, or whether we are looking upside down, or whatever the frame of reference you choose, the state is the state. And if you want to look at it in the position basis, right, in position basis, so this is, what do? We project this state to the basis we are working with, which is the position basis. So we are kind of like looking at x component. And how do we do this? We know how to do that. We take the state, which is psi of t, and we take inner product. That's how we make the projections. And this thing we are going to define to be psi x comma t, the real space wave function, right? The wave function we said earlier is nothing but components of the state in the position space. Okay? So here I want to just, if you are following the book, Griffiths is using like something like S here. But I'm not, we are like more familiar, I'm more familiar with this notation where we use the state itself. I mean, if you like that, you can just replace all of my psi's with S, and everything we say is going to be unchanged. Similarly, there's nothing about position basis. We could also be, I mean, in our life, we happen to be in the real space. But there's a symmetry between real space and momentum space. I can also write things in the momentum space. And the similar argument is going to be P component. And for that, we just do exactly the same thing. We take P, like bra P, and take inner product with ket psi. And this object, earlier, a couple of lectures ago, we defined it to be Fourier transform of wave function. This is PT. So we could do things in the energy basis, like suppose I want to look at it in some n basis. N can be energy or some other basis that is given to us by our problem. Then what we do is we just do it n, this psi of t is equal to, this is what we call expansion coefficient, right? Good, so this is what we are working with. We have like an abstract state, and this state can transform to different bases. And what do we have in this space? We have operators, which are going to be observables. And operators transform one state to another. Like some mysterious sentence, but don't worry, I'll talk about this. So suppose I have like a state alpha in my Hilbert space, and I have some operator. Now my operator is also abstract, independent of the basis. I can have like a observable, right? Whether I'm in momentum space or real space or in energy basis, doesn't matter. Observables are observables, and they all have like some abstract operator. By hitting on my state, I am going to have another state in the same space. And the key is alpha is in the Hilbert space, and beta is also in the Hilbert space. And in the given Hilbert space, I can also have an orthonormal basis, because any space can have like a basis. For example, for alpha, I can just expand it in some an, en. And what is the expansion coefficient? Expansion coefficient is immediately en alpha. And here, my orthonormal complete basis is denoted by these ens. And similarly, I can do the same thing for beta. So this is going to be some bn, en, and the expansion coefficient is immediately en beta. Then I can try to express this abstract relation, a state is equal to an operator times another state in the given basis, like this guy. So beta is this thing, is equal to this q times alpha is this thing, and I can like, so this is just expansion coefficient. This operator is going to go and hit on the expansion basis element. So this is going to be sum over n, an, q, en. Now I can take inner product with some bm on both sides, like hit with em on both sides. Then on the right hand side, on the left hand side, I have em times en, which is orthonormal, and it's going to give me like a Dirac delta function, and the delta is going to cancel summation. At the end, I'm going to have this bm is equal to, on the right hand side, I'm going to have this an, em, q, en. So this q is operator. So at the end, you can see we have like an object with two indices. So this is, let's call this q m n, And the QMN is defined by this QMN, like E1, Q, E1, dot, 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 E1, Q, EM, dot, 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 EM, Q, E1, dot, 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 EM, Q, EM. Because it has like two indices, I wrote it in the matrix form. And we can see this expression, this last expression, is in the form of like a Q matrix. Let me write it like this, times a column like A1, A2, dot, 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 AM. And each component is going to give me like a B, so it's going to be B1, B2, dot, 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 BM. So what we did is like we had like an abstract operator. By studying its effect on basis states, we transformed the solution to matrices and to linear algebra. Now we are working with matrices rather than some abstract objects.
Hocam, is that n by n or n by
Yes, this is m by m, right? Because there's this ket has like m different elements. Bra has m different elements. So the matrix is m by m.
We didn't say mn.
Mn, I think let me say it this way. Yeah, thank you. Let's call my basis is like something like this. N 1 to dot 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 uppercase n. Let me fix that notation. Then this is going to be n by n, right? This is n, and this one is n by n. Yes, thank you. I appreciate. Now, if we can express the states in different bases, we can also express the operators in different bases, right? And a quick example of this is like, for example, x, the operator is position. That gives us the position of our state. If we are in the real space, it's just going to be coordinates x. And if we are in the momentum space, it's going to be I h bar del del p. Right? Exactly the same abstract operator has different appearance depending on the space. Similarly, p is like an abstract momentum. And if we are in the real space, we know it is minus I h bar del del x. And if we are in the momentum space, this is going to be just number, p. So there's a little bit technicality that I should just let you know. So from a technical point of view, so this bra, like let's say some function bra f, is a linear function. Actually functional, but the book says function, so I will say function. And what is a function? Function is an object that takes something and spits out a number. In this case, this f is going to take a ket, something like, I don't know, g, right? And if you want this, sometimes people use this notation, f takes g, and the meaning of this is like you do this, and this is just a complex number. But for those of you who are mathematically inclined, there is like something called Reed's theorem, and it says the ket space and bra space are in one-to-one correspondence. They're exactly the same. Okay, mathematicians figured that out. Generally, physicists don't care. They just do their calculation. From that point of view, this bra f is dual space of f. Okay, so that means they are isomorphic to each other. They are exactly the same thing. Okay, it's a little bit mathematics. I myself don't like mathematics. If that intimidates you, no worries, right? The calculation, we already figured it out. It works out. So now consider the expansion. So this abstract state, I can expand it in any state, and let's expand it in this Cn n basis. And we already said this Cn is just n psi, right? That's how we find the expansion coefficients. Let's plug this in. So then this thing is equal to n psi n. And naively, like, yeah, this is like a C number, and we can move numbers around. It doesn't hurt. So I can write it like this. So I just didn't do it. I just wrote one thing after another. And now if I looked at this expression, so I have 1, right? There is like 1 multiplying psi here, and something else is multiplying psi here. And from here I can say if they are the same thing, right? It is like an equation. Then I can just write n is equal to 1. Right? This is like a one unity, like a, if you want, it is like unit matrix in n by n matrix. So this is sometimes what we call completeness relation. Good. Any questions?
I didn't understand when you change the ncat and ncat and beside.
So this I said. So this piece. So this is written as n psi, right? This Cn is just like a number, right? It's like a complex number. I can write it here. I can write it here. I cannot write it outside the summation because it depends on the summation index. So if I write it here, so this is going to be n psi. It's exactly the same thing. And from there, I just combine this n-dependent piece in one package, and this n-dependent piece in the package is should be 1 if left-hand side is equal to right-hand side. Now, if we can do this in the n basis, we can do it in the position basis. So, in position, we have some operator x, right? X is an observable. If it's an observable, it's Hermitian, and Hermitian observables have complete set, right? They have real eigenvalues, and their eigenstates are complete. And for the x, all of these things we said are valid, and we can label its eigenstate with the position x, and this is going to give us the number x times x. And they should be also be orthonormal. If I take an x and an x prime, this is the inner product between two different vectors in the Hilbert space x labeled with x and x prime, and it should be x minus x prime. And I can also expand my wave function psi, right, in dx some c of x, and we know expansion coefficient is x psi, and by doing exactly the same trick, I can just get minus infinity to plus infinity dx x is 1. If If I can do it for position, I can do it for momentum. The same thing. So this is P, P, and P. And any inner product in the abstract Hilbert space, I can have, right, a bra in the Hilbert space. I can have a cat in this Hilbert space. And this is the inner product, the abstract inner product in the Hilbert space. I can write it in any basis I want by using these completeness relations. I can just insert here a unity of any unity I want. For example, let's insert unity in the X space. That's how I use the unity is the unity, but we can choose it, how to express it, right? This is going to be dx minus infinity to plus infinity. This is psi 1 x psi 2. So this thing is what we define to be psi 2 of x, right? Because this is the expansion coefficient, which is the wave function. And this thing, we can use x psi 1 complex conjugate, right? For any alpha, beta, star, I just replace beta and alpha. Then this thing is psi 1 of x star. Therefore, this object is dx psi 1 star of x, psi 2 of x. The inner product we defined in the Hilbert space. Good. Now I can let's consider this psi of x, which is equal to x psi. And I want to insert here unity of momentum. Let's put 1p is going to be dp from minus infinity to plus infinity x p psi. This is what we called phi of p, the expansion coefficient in the Fourier space. But from the Fourier transform, we know this is also equal to dp e to the I px over h bar divided by 2 pi h bar times phi of p. Right? This is the Fourier transform we used before anything else. By comparing this line and this line, right, this is phi p here, integral, the same integral, minus infinity to plus infinity, then this object and this object should be identified. Right? Then the inner product between x and p is e to the I p x over h bar divided by 2 pi h bar. So if you forget it, that's how you derive it, right? Sometimes I forget, was it px or xp? You can always just do these 2 lines of calculation and derive this relation. So let's do an exercise. Let's calculate position operator in momentum space. What I mean is, I have a state psi, and on this psi I want, right, this is abstract state. I hit with my operator an abstract operation, and now I project it in the momentum space. That's the definition of like momentum measurement, right? Position measurement in the momentum space. Then this is going to be equal to, let's put unity here. So this is 1p. But because I am going to operate with x, it's actually better to do the x unity, right? Then this is going to be dx minus infinity to plus infinity. This is p, this is the x operator, this is xx, and this is psi. Now this piece is my wave function. So this piece, x times x is x. Now this x is a number. It can go around. So this bigger piece is going to be x px. And I just derive this, right? Then this entire thing is going to be equal to dx minus infinity to plus infinity x. So this is xp. I have px here. I just need to take complex conjugate. This is e to the minus I px over h bar over 2 pi h bar. And this is psi of x. Good. But this thing, right, this thing, there is only one p dependent thing here. I can write it as del p. If I take the derivative, it's going to be minus I x over h bar. So I need to multiply with h bar, and I also need to multiply with I. Then this thing is going to be, right, this is now, I can take this outside the integral. So this thing. And what remains is going to be our Fourier transform. Right? So this is our phi of p. Then we conclude x phi of p is going to be I h bar del p phi of p, which we found previously by using some other trick like biparts and stuff. So as an exercise, you can try. So here's your exercise. Show using exactly the same trick, you can calculate this x p x prime to be equal to minus I h bar del x delta of x minus x prime. Here you need to insert two unities. One unity will not do it. Okay. Any questions? Now let's think about this expansion. Like this psi is equal to n psi. Right? We are putting unities wherever we want, and you can be generous as many unities as you want. From here we can see if I defined an operator p with the index n, so this n, what does this do? So this guy hits on anything, right? It hits on anything. Let's try, like Pn times m is going to be n m. So this is what? This is delta nm. Then this is going to be delta nm times m. So it hits on anything, and if the index is equal to what you are trying to project, it picks it up. Otherwise, it gives 0. It's like projection, right? So it's like a projection operator. So this is projection op. And it has some properties. For example, if I have two of these, if I project Pn and Pm, what is it? It is n, m, m. So this is delta n, m. So this is going to be delta n, m, n, and this is equal to delta n, m, Pn, which also shows me like this Pn square is what? N, a lot of n's, but it is also n, which is Pn square is equal to itself. Yes.
Hocam, why do you write n after projection line?
So this one?
Yes, at the end we write n.
Oh yes, this is n. Because delta nm, right? It doesn't matter.
But it's directly equal to n can't n, right? Like,
So I wrote it like so n. So this is the inner product. From the inner product, I have delta nm, which is here, and what remains is this. But the thing about delta function, if you have like a delta function, you can write it n or you can write it m. Doesn't matter. But I think n is probably better because we are trying to project it on n. This one? So this is nm, nmm, so this is delta nm. And I said yes. So this is delta nm. And this is actually something like this, right? Delta nm m. But since n is equal to m, I just wrote n. Yeah, same thing. I'm rewriting the same thing. And this one also, I think, just exactly the same thing, right? Take n is equal to m here. Pn square is going to be Pn. And if you sum over everything, right, this Pn, sum n, Pn, this is the unity. Now we can connect these things. Let me do one abstract, one example of this abstract thinking. Let's calculate expectation value of H. Right? This is going to be our energy expectation value. And we know this is, right, if you want, I can do it, but we did it many, many times. So I can just write the result. So this is the expansion coefficient squared times En. Right, we did this. And the expansion coefficient is what? It is n psi squared. And I can write this as, okay, let me do it in 2 steps. So I'll do this. So this is something times its complex conjugate. Complex conjugate is going to be n psi. And now I do it one more line. So this is, I can take this psi out. Psi, sum over n, En, and the other psi. Good. And from here I identify this H with this, if you want, so-called spectral decomposition, if you want to sound fancy. But the Hamiltonian is decomposed into its components in your basis. Good?
Actually, it's a diagonal map.
Yes. So the operator here, if you remember, this operator was not diagonal, right? This one, because we were not in the basis of this operator, but here we are in the basis of eigenstates, energy eigenstates. That's why Hamiltonian is diagonal. But it is exactly the same logic, yes. So let me show one last thing here and I'll finish after that. And in the second hour, maybe I can give you like an example application to make all these abstract things a little bit more practical. So let's think about time evolution. So now the abstract notation is I h bar del t, this psi of t acting on h psi of t. So this is operator in H, and this is a state in Hilbert space H. And I can solve it, right? The solution is e to the minus I over h bar operator h times t hitting on psi at 0 is my solution, psi of t. So how do I know this? First, to write this, I'm assuming h is time independent. If h is time dependent, you can do something a little bit more complicated, but formally the same thing. If h is time independent, I can just take del t psi of t is equal to e to the minus I over h bar h times t minus I over h bar h psi of 0 that has nothing to do with time, right? Now this h and this function of h commutes, right? For any operator, take a function of operator and operator, they always commute. So maybe I can give you as an exercise, convince yourself. And if this is the case, I can write this as, right, I multiply both sides with I and h bar del t psi of t is equal to this h times this thing, but that thing is definition of psi of t, so I have psi of t. Good. And okay, let me say one last thing and then finish it there. Any function of operator, we think of them as a power series so that we can apply them one by one. What I mean is e to the minus I over h bar h times t, this formal thing, is by definition n is equal to 0 to infinity 1 over n factorial minus I over h bar h times t to the power n, right? And you can see to get the full time evolution, I need to apply h infinitely many times. In the lowest order, I have like 1 power, in the second 2 powers, 3 powers, right? So this is what we call power series. And this is not for just h. For any operator, if you have e to the q, this is defined as q plus, okay, 1 plus q plus q square over 2 factorial plus dot dot dot. If you have 1 minus q, this is the geometric series. If you want, this is 1 plus q square plus q cube plus dot dot dot. And if you have, I don't know, log 1 plus q, this is going to be, how did I do it? Q minus a half q squared plus 1/3 q cube dot dot dot. Okay, any questions? So in the second hour, I want to show all of these things for the simplest possible system, a 2-level system, and hopefully all these abstract objects are going to be a little bit more concrete. Okay. Thank you.